All right, hey, welcome back, you guys. Here's the part two for our Kinetics Day 3. We're going to talk about reaction mechanisms and I can't say it, catalysis, okay, whatever. Basically, it's the use of catalysts in reactions. And you may be familiar because you guys, I know, have all taken biology with catalysts. Another word in biology for a catalyst is an enzyme. So an enzyme is a substance that speeds up a process biologically. Okay, in chemistry we call those the catalysts. Okay, and so it's a way for us to affect the rate of a reaction. Okay, we'll get into that towards the end of this show here. So first thing I want to talk about though is reaction mechanisms. So we need to understand this, that most reactions don't happen in just one quick step. Okay. They usually occur in two or sometimes more steps, but more often it's two. So we've got this basic reaction right here, okay? And we have this mechanism where we have two steps, right? Where the two NOs form dinitrogen dioxide, and then that dinitrogen dioxide reacts with the oxygen to form our two nitrogen dioxides here. And if we look at this, overall, we get the N2O2s canceling out. So even though they're present, they are not really a product or a reactant in the reaction. So what are they? Well, here's the deal. They are what is called a reaction intermediate. Okay. So a reaction intermediate, that's a substance that's produced and then it's consumed. So here we get N2O2 is produced. The first step of the reaction, and then it is consumed in the second step. So what's the intermediate in this reaction? It is this right here. Okay, produced and then consumed. So it's not a product or a reactant, it's an intermediate. Okay. Now, how do we determine the rate law? So it's really important for us to understand that to determine the rate law for a reaction, we have to do that experimentally. And those are the things where we've been looking at data you guys produced experimentally and saying, oh, well, when we doubled A, we doubled the rate of the reaction. So it must be first order, okay, and so on. So we can only do that by experimentation. So for instance, for this reaction right here, we found by experimentation that when we doubled the concentration of NO2, we quadrupled the rate of reaction. So that's second order, right? However, we found this, no matter what we did to the concentration of carbon monoxide, it didn't affect the rate of the reaction. So therefore, our rate ends up being this here. Because remember, if it's zero order, anything to the zero power is 1, right? So that's not going to affect the rate at all. Okay, so now, determining the rate law. We did that. But how can we know the rate law if we know what the elementary steps are? So what I mean by elementary steps is those two steps that lead us to the reaction. So here's step number 1, and I'm just going to put everything up here, you guys. Okay, the rates of these elementary steps are predictable. So if we look at this one, the rate, okay, is basically this. It's NO2, and it's second order because I've got a coefficient here. So that's my rate there. If I look at the second step, my rate is going to be the concentration of NO3 plus carbon monoxide, concentration of carbon monoxide. Okay. Now I want you to notice this though. The step 1 rate law is the same as the overall rate law. What's up with that? Okay. And remember this. This is when I do this, this is only for elementary steps. We just take the concentration and we raise the coefficient as a power. Got that, you guys? Okay, so these elementary rate laws are predictable. We can't do that with an overall reaction. All right, so what the deal is this, right? Step 1, there's is slow, so that means it takes a while. Step 2 is fast, so it happens instantaneously. And that's the way that almost all of these reactions are, you guys, is you end up with, out of the 2 steps, a slow one and a fast one. Okay. And I'm going to apologize for this typo here right now. There should be an R right here. Not the fate of the slowest step, the rate. Although I guess fate isn't quite that far off, is it? Okay, so if we look at things, the rate of our slow step the rate law is going to be the same as the overall rate law for the reaction, because that slow step is going to determine the speed at which the reaction proceeds. Okay, so we're going to determine the rate law. So here we have a new reaction, you guys, right? 2 NOs plus O2 gives us 2 NO2. Here's our first step, okay? And if you notice, it's equilibrium, right? It's equilibrium, and it's fast, and it's reversible, okay? So this reaction can go back and forth, okay? And here's step 2. It's slow, so it only goes forwards, right? Now I want you to notice something. This should be the rate law, right, you guys? Because this is the slow step. However, we've got this issue. We can't know what NO3 is, the concentration of it, because it's an intermediate, isn't it? It gets produced in the first step and consumed in the second. So we can't find the concentration because it never really exists, right? As soon as it's produced, it begins to be consumed. Okay, so yeah, so how do we figure that out? So here's the deal. This is where this is going to get kind of tricky, you guys. Okay, that should be the rate law. How do we get to a rate law that makes sense? Okay, whew, tricky stuff there that I did too, huh? All right, so solving the problem. Here's the deal. First thing we need to do is take this guy here. Okay, we know the forward rate is that. Okay, the reverse rate, when we go this direction, okay, get my pen out here. So the forward rate here, that's when we go this direction, right? That's our forward rate law. Okay, our reverse rate law is going to be this direction. Okay, and so we can kind of start to use this because at equilibrium, these two rates are going to be equal to each other, right? Remember, at equilibrium, the forward and backwards reactions occur at the same time, at the same rate, right? Okay, so we've got two rate constants. We've got a rate constant for this guy, a rate constant for this guy, and we've got our concentrations. They should be equal at equilibrium, right? Okay, now we're going to solve for NO3. So I'm just going to divide both sides by K2, right? So now I know this. The concentration of NO3 is going to be equal to two rate constants times the concentration of NO times the concentration of O2. Okay, so there's where I start to set this up. So now we've got this guy, right? Here's our supposed rate law down here. Well, hey, now I know what NO3 is equal to. Okay, if this gets complex, drop in on me or ask some questions, okay? We'll do some chatting about this on Thursday, or if not before. Okay, so solving the problem, we know this, right? NO3 is equal to this. Okay, so let's substitute it in. Replace NO3. So I get this, right? I get this guy right here. Now this looks complex with all these K's, right? Really what this means is, remember, for every reaction, you guys, for every reaction, we get a, we basically get a new rate constant, right? Okay, so I get this here. Ooh, and if I combine these NOs, boom, I get this. Here's my rate. My rate is K, our new rate constant, right? Okay, which is a combination of all these. Let's clean that up and just make it, hey, it's a new one. But NO squared, okay, second order times O2 to the first order. Okay, that seemed complex. Whew. I pretty much, you know, I'm thinking they probably won't give you a problem like this in the AP exam, but I want you to be able to kind of logic your way through this. So check out the slideshow, and if you need to print it off and take a look carefully, let me know. Okay, and then ask questions. We'll be getting together this week like always, and we can talk through it. Okay, now let's move on to something that's a little bit easier to understand, you guys. Okay, catalysts. Okay, so a catalyst is a substance that speeds up the rate of a reaction by participating in the formation of a new intermediate in the reaction. Now here's something that's really important. Okay, catalysts are not produced or consumed by the reaction. Okay, they just participate in it. And the big thing that a catalyst does is it lowers the activation energy. If you remember back to the first video, if we lower the activation energy, you guys, what happens to the rate of the reaction? Nice job. If you said it goes up, that's right. Okay, so right here, right, we can see how the activation energy without a catalyst is much higher than it is with a catalyst. When we put that catalyst in because of the lower activation energy, we get a faster rate of reaction. Woo! All right, so this is our kind of our last slide here, right? Here's an example destruction of ozone. This used to be a huge deal, you guys. Chlorine from chlorofluorocarbons, okay, that we used to use in refrigerants would get released into the atmosphere, head up into the stratosphere, and affect our ozone layer, which is a huge part of protecting us from UV rays. So the chlorine here, right, would act with the ozone, okay? It would form an intermediate, okay? And that intermediate would react with the free radical to form O2, okay? And the chlorine is still there, okay? And I've heard this, you guys, that a single chlorine atom like this can degrade up to 100 ozone molecules before it reacts with something else and moves on. So what's the intermediate? The intermediate, you guys, is this right here, right? Okay, the ClO. That's our intermediate. Okay, what's the catalyst then? So the catalyst is the thing that participates in the reaction but does not actually end up getting changed by the reaction. That is the chlorine. Okay, you notice it's there in the beginning, it's there at the end, right? That makes it a catalyst. An intermediate is there in the middle, okay, but not at the beginning or the end. Okay. Now, if we were to write out this reaction, you guys, basically chlorine would not be part of the reaction because it cancels itself out on both sides, right? So even though it participates, it's not part of the reaction because it actually doesn't get changed in the reaction. It just helps in the formation of an intermediate. Well, that was a lot, okay? So if you've got questions, email, call, drop in on office hours and stuff like that, you guys. I will be posting Zoom links and stuff like that for you to get in touch with me. Well, thanks for tuning in, you guys. Hope you had a great weekend.